You're going to need to know some general information about alkanes, and also remember you need to know and be able to recognize your functional groups. So don't forget to study those functional groups. Among the ones that we're most concerned about at this point, you're going to need to know what a carboxylic acid is. This is very important, especially if you're going on to get into the medical field. You're going to need to understand carboxylic acids and amine groups, because these form proteins, or they're amino acids. So if you remember from your biology class, an amino acid has this at one end, it has something else in the middle, and this at the other end. So we'll be doing a lot with these two. Also recognize that this is an aldehyde. The difference between this one and this one is there's only a hydrogen here instead of a hydroxide group. Then you need to know an alcohol. Now, that's not to say that these are the only important ones, but these are definitely ones that you have to know for this test. Also, just general information about alkanes. Remember, organic chemistry is carbon containing, except carbonate ion is not considered organic. So for example, especially in this area where we live, there's a lot of limestone. Those rocks contain carbonate. Rocks are not organic, and carbonate is not organic. But organic chemistry is chemistry that contains carbon, except for the carbonate. Now, very important to understand that carbon forms 4 bonds. So when you're drawing your structures, you're going to need to make it have 4 bonds. It could have 4 bonds, and some of them could be double bonds, there could be triple bonds, but remember, 4 bonds. Also, remember that this symbol, this delta positive, means partially positive. So, for example, if we take a carbon and bond it to a halogen, in this case chlorine, this end would be partially negative. Draw a divider line there so that you don't think that that's a positive end. Chlorine is very electronegative, as are the other halogens. This end is partially positive. And in organic chemistry, a lot of times we will symbolize that. Instead of putting the delta negatives and delta pluses, we'll do it like this. We have an arrow, meaning where it's pointing is partially negative, and then this little plus sign here shows that it's partially positive. Properties of your alkanes. Just think of gasoline. Gasoline and other alkanes have low melting points and low boiling points. They tend to be insoluble in water. So you're not going to be able to dissolve your gasoline in your water. Your gasoline evaporates very easily, has a low boiling point. It is very hard to freeze because it has a low melting point. You're going to find this with other alkanes. Another important thing about these alkanes is that as the number of carbons increase, the melting and boiling points increase. So that is a direct relationship. If you, I don't know if you had this in your math class or not, or in another chemistry class, but that means direct relationship. So as the number of carbons increase, so does your melting and boiling point. There are other properties of alkanes, but these are the ones that just come to my mind right now. Now, another important thing is to be able to recognize isomers. The trick in recognizing your isomers is that they have the same molecular formula, but different structures. So if you have a problem that asks whether something is or is not an isomer, then what you would need to do is look at what's given to you, and you're probably going to be given a line structure. So let's do this line structure, and let's do this line structure. Make sure I've got it drawn correctly. Okay. Now, you're going to have to remember that each one of these little intersection points is a carbon, and that carbon has to have 4 bonds. So while you're new at doing this, you might want to go ahead and put a dot on each intersection point just to help you know that that is a carbon. I'm going to do the same thing for this structure here. Now, knowing that carbon is going to form 4 bonds, there's 1 bond on this carbon, so we have to add 3 more. There's 2 bonds on that carbon, so we're going to add 2 more. This is a tertiary carbon because it's bonded to 1, 2, 3 other carbons, so there's only room for 1 more bond. This one is bonded to 2 other carbons, so there's room for 2 more bonds. This one is only bonded to 1, so we can put 3 more bonds. Same thing here, it's only bonded to 1, so I can put 3 more bonds. So when you double check, you want to make sure that everything, all of your carbons have 4 bonds. Hydrogens, when it comes to these line formulas, hydrogens are understood. It would be terrible whenever we start getting to very large structures to have to write out every single hydrogen. But while you're in your learning stage here, it might be helpful to just do that. So when you count up, an alkane has only the carbons, well, this alkane has only carbons and hydrogens. So 1, 2, 3, 4, 5, 6 carbons, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. I'm going to count that again because you know these things get a little bit tricky. The hydrogens tend to mess with your mind a little bit. Got 1, 2, 3 times 3 is 9. That's 10, 11, 12, 13, 14. Okay, so this is the molecular formula. And just as a reminder, the empirical formula is going to be the smallest ratio here. Both of these can be divided by 2, so I get C3H7 is the empirical formula. The purpose of this empirical formula here is very simply to give you a ratio of each element present. And this is very frequently used whenever you're doing a lab or if you're working in a laboratory where you have to analyze what something is made of. So for example, when the police look at forensic evidence, a lot of times they'll put it through a type of machine and it'll spit out a ratio. It's not always going to just spit out, well, these machines that they have, they're never going to just spit out molecular formulas or structures. The chemists have to take this information and some other information, put it together and try to, knowing what they know, make the structure and figure out what it is. So this is very helpful and very practical in the analysis. I don't know if that's how you spell it, but that's what it's used for. Let's come back up here and determine this empirical formula, or excuse me, molecular formula. So I've got 1, 2, 3, 4, 5, 6 carbons. There's one bond, so I can put 3 more. This one is a tertiary carbon because it's bonded to 1, 2, 3 other carbons, so I can only put 1 more. This is only bonded to 1 carbon, primary carbon, so I can put 3 more. Secondary carbon because it's bonded to 2 other carbons. Another secondary carbon, and this is a primary carbon because it's only bonded to 1. So if I go ahead and add my hydrogens here, I've got 3, 6, 9, 10, 12, 14. I'm going to count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, yes, they do have the same molecular formula. So they are isomers of each other. Now, they have different structural formulas, meaning that they're put together in different ways. And the way that they're put together means everything, because the shape of the molecule determines how something is going to behave, how something is going to react with something else. They can't have conversations, so they can only do what they do by means of what their shape will allow them to do. So notice that this one is attached to this middle carbon, okay, and this one is attached to this second carbon. So they are not going to behave in the same way, but they do have the same molecular formula, so they're isomers of each other. While we're at it, let's go ahead and name these. Remember, when it comes to naming, you have to find the longest continuous chain. So we've got a few different parts to a name. The first part of the name is going to be the substituents. We need to know what they are, their identity. and their location, and how many we have. So part of our name is going to be telling us what the substituents are, where they're located, how many. Another part of our name, this is going to be the second to the last piece of the name. This tells us how many carbons are in our parent chain. So this is going to be like, if it's 1 it's methyl, 2 it's ethyl, 3 propyl, 4 butyl, 5 pentyl, pent, and so on. Okay, here this is the type of bond. Since all of these are single bonds, we have no double bonds, no triple bonds, the last part is going to be ANE, ane. Now when we count our parent chains, we got to get a little bit, treat it kind of like a puzzle, because sometimes these parent chains, this one's not going to be very hard, but some of them do get difficult. We got to count them in different ways. So on this one, if we were to count 1, 2, 3, 4, 5, if we were to count it this way, we've got 5 carbons as our parent chain. But we want to see if it makes a difference doing it this way. 1, 2, 3, 4. Nope, we still want to go with the highest consecutive number of carbons, and that's 5. Okay, let's try this way. 1, 2, 3, 4. Nope. So this is going to be our parent chain, the longest consecutive number of carbons in a row. So that one's pretty easy. 1, 2, 3, 4, 5. So it is some type of pentane. Alright, now we got to look at our substituent. It doesn't matter whether in this case we begin numbering from this end or this end, because it is right in the middle. And you'll see that if we number from this end, 1, 2, 3, 4, 5, will be the same. It's on the third carbon, and that will be the same if we number for this end. 1, 2, 3, 4, 5. So no matter which way we number it, we're going to get this substituent at the third carbon. Remember, the way that you number them, the substituent or the group that you have has to be at the lowest number, and they have to be in alphabetical order. So this substituent has 1 carbon. It is a methyl substituent. So we've got the name meth because it is 1 carbon, and because it is a substituent, it is not called methane, it is called methyl. So we could name this 1, 2, 3 methyl pentane. Okay, so this would be called 3-methyl pentane. Now let's take a look at this one. Another thing that we can notice right here before I move on, do you see how this substituent, it is the same on both sides? Okay, so if we're only looking at this substituent right here, and we're seeing that what is on this side is equal to what is on that side, we can, in some cases you'll see things named this way, but we have a prefix that means equal, and that is iso. So you've seen this before when you were naming some substituents like isopropyl, isobutyl. Another thing that you might see is you might see this being called isomethyl pentane. And when you put the iso in front of the methyl like that, you do not have to put the 3 in front. If I were you and I were taking a test, I would stick with my numbering system instead of having more of a possibility of making a mistake with iso for equal on each side, sec for secondary, tert for tertiary. If I could stick with my numbering system on this, I think you'd have a better chance of not making some mistakes at this point. Now let's go ahead and name this one. Again, the longest chain, we're going to have to count both ways. If I count this way, 1, 2, 3, 4, 5. And if I count this way, 1, 2, 3, 4, 5. So it doesn't matter which way I count. So I'm just going to count this way, so it'll be a little bit different from what I did on this side. Again, we have a methyl substituent, and we're going to number it such that it is at the lowest carbon. If we number this way, this carbon would be 1, this would be 2, this would be 3, 4, 5. So if we number this way, it would be 2 methyl. However, if we were to number this way, this would be carbon number 1, carbon number 2, carbon number 3, and this would be carbon number 4. It would be 4 methyl. So we want to number it this way so that this substituent is given the lowest number, 2 methyl. Okay, not 1, 2, 3, 4 methyl. Not 4 methyl, but 2 methyl. And again, it is pent because there's 1, 2, 3, 4, 5 carbons in a row, and it is ane because there are no double bonds and no triple bonds. We're going to take it one step further here, things that you need to know for this test, and that is calculating the molecular weight of something. This is pretty easy at this point, but I just want to make sure that we're able to do it, because we've got some labs that it's going to make that very important. So the molecular formula is the same, the molecular weight will be the same. Okay, so I'm going to use the abbreviation MWT for molecular weight, but remember, sometimes you'll hear gram molecular weight, you might hear formula mass, molar mass. There's all kinds of things that a person might get lazy and say right here. Sometimes GMW, gram molecular weight. So the proper term would be molecular weight, because this is a molecule, it's organic. But remember, sometimes people get sloppy and they use other words like molar mass or molecular weight, or all kinds of things. You have 6 carbons, so that is 6 times 12 grams per mole. Yes, I do need to see that you're using the units in dimensional analysis. I believe 6 times 12 would be 72 grams per mole. We have 14 hydrogens, which is 1 gram per mole. So that gives us 14 grams per mole. Now we're going to add these together, and I believe that would give us 86 grams per mole is our molecular weight of this particular formula. Let's go ahead and take this just one step further, since we're going to be doing this on the test and you're going to be needing to do it in labs. And let's just say that we need, so we've got this question, what is the mass of 3.2 moles of, I would probably give you the name, let's just say 2-methylpentane. So when you have this question, remember that you're going to have to first of all take the name and get the structure. Then you're going to have to take the structure and get the molecular formula. We've already done all that. From the molecular formula, you need to know the molecular mass. And we know that the molecular mass is 86 grams per mole. Again, I need to see that you can use your dimensional analysis. We have 3.2 moles. We're given 3.2 moles. So that's what we're given. Remember, we're going to put that over 1 just so we have an up and a down, top and a bottom. We're going to put this in and we're going to leave it because we want to cancel moles and end up with grams. Okay, so when both of them are on top, you're simply going to multiply 3.2 times 86, 3.2 times 86, and I get 275.2 grams. Now, when we're just doing problems for organic chemistry in the book, not in the lab, but in the book, I'm not, unless I specify, I'm not going to be picky on the significant figures. If I were to be picky on significant figures, then this would end up being, with 2 significant figures, it would end up being 3.8 times 10 to the second grams, but there's a reason why we're not too worried about that right now. Your mind is already going to be tasked to its fullest just getting to this point. So while we're taking tests and while you're doing homework, unless specified, I don't need to see this. I just need to see this. Alright, I know you think you're almost done, but let's just take it one step further. Let's just say that you're trying to prepare a solution that is 0.5 moles per liter. And you want to know, since we don't have a scale that can weigh that, you want to know how many grams should be added to .5 liters. So in other words, you want to make 500 milliliters. You don't want to make a whole liter. I'm not going to have this particular one on the test this time, but might as well go ahead and look at it while we have all this information laid out for us. This is what we're given. This is what our conversion factor that we're given, we start out with, and we're also given this part right here. This is how much we need. So if I take this, so this is a conversion factor. We can look at it like a conversion factor. It's the desired molarity that we need. And we can look at this one, even though both of these are given to us, this is what we're going to start out with, 0.5 liters. We're going to put it over 1. Then I know I'm going to need grams. So if I look back to information I have, this is 86 grams per mole. Okay, so 86 grams per mole, and this is the GMW, the gram molecular weight. It's also a conversion factor for us. So if I want to get rid of my liters, I can use this particular term to get rid of liters and end up with moles. So if I leave it and don't flip it, I'm going to end up, my answer would be in moles. Now, I don't want my answer in moles, I want my answer in grams. Now I can use the GMW, or this particular conversion factor, plug it in, 86 grams on top, moles on the bottom, to figure out how many grams I would need. So if I took 0.5, they're all on top, so I'd multiply 0.5 times 0.5 times 0.86, or excuse me, times 86. 0.5 times 0.5 times 86 gives me 21.5 grams. So in other words, I would take 21.5 grams of that and put it in a container with something that it dissolved in, so that the final volume was 0.5 liters, or in other words, 500 milliliters.